Did you know that the stars, under their destructive airs, produce, in fact, the elements which compose our universe? As physicist Hubert Reeves said, we are all stardust. Intriguing, isn't it? Yet this is only one of the many mysteries that revolve around these molten stars. The stars are at the origin of many myths and beliefs. In ancient Egypt, the sun was the incarnation of the god Ra, crossing the heavens in his boat, creating the day-to-night cycles. Among the Incas, Inti was the god of the sun, source of heat and light, protector of the people. He was considered as the most important deity. Even the Greeks, though far ahead of their time, considered the god Helios as the personification of the sun. He and his sisters, Selene, the moon, and Eos, the dawn, gave rhythm to the life of the Mediterranean people. Today, our knowledge and observations of the sky have allowed us to learn more about this star. At first considered unique, we know that the sun is only one star among many others, a simple drop of water in an ocean of celestial bodies as massive as luminous. And yet, to say so is a sweet euphemism. According to the latest observations, our Milky Way is home to between 200 and 400 billion stars. But it, too, is only a simple galaxy among the thousands of billions that are hidden in the observable universe. Astronomical figures, which if we think about it too much can make us dizzy. Even the most starry sky reveals only a tiny fraction of the stars in the cosmos. If all of them were visible, we would be constantly bathed in a blinding light day and night. Dear traveler, welcome. Today we are going to discover these balls of gas through a journey to the edge of our universe. During this space odyssey, we will discover the multiple faces that these stars can take. We will dissect their life cycle, from their birth to their death. A scenario with various outcomes, sometimes cataclysmic, sometimes poetic, but always surprising. We will also make some stops to observe the most intriguing stars ever discovered. Some are still a mystery to science. Before you leave, think about liking the video and subscribing to the channel so you don't miss anything. So are you ready to embark on this fabulous journey? Our adventure starts now. Jupiter, our neighbor, is what we call a gas giant. It is the largest planet in our solar system, with a diameter 11 times that of the Earth. However, it remains tiny compared to our Sun. The latter is 10 times larger than Jupiter. This disproportionate size explains why the Sun appears so clearly to us, even though it is about 150 million kilometers, or 93 million miles from Earth. On a human scale, the Sun's proportions are immeasurable. Yet our star is considered tiny in comparison to the entire cosmic bestiary. Astronomers call it a yellow dwarf, a nickname that seems exaggerated as it minimizes its proportions. And yet, this term perfectly describes our star, given the gargantuan dimensions of some of its peers. That said, there are also stars smaller and less bright than the Sun. So to begin our journey, let's discover the different types of stars that populate the galaxies. You will see that some of them are quite different from our star of the day. Earlier, we talked about our neighbor Jupiter. This planet is impressive, but it is far from being able to claim the status of a star. However, some observations show that the fifth planet of the solar system could have become a star. Moreover, there are similar stars in the universe. Halfway between a gas giant and a sun, these strange bodies are called brown dwarfs. Also known as failed stars, this pejorative term reflects their situation. Indeed, brown dwarfs are not really planets, but not really stars either. They have a size similar to our dear Jupiter. But the minimum mass of a brown dwarf is about 13 times more massive than Jupiter. Unfortunately, their mass is not sufficient to trigger the fusion process. In other words, the pressure in their core is not sufficient to fuse atoms, as is the case in other stars. Thus, we can say that these stars have never succeeded in lighting up. Just like an aborted attempt to produce a wood fire, leaving only a cloud of smoke without flames. Quite hot at the time of their formation, they gradually cool down and shine less and less. Brown dwarfs are therefore quite difficult to detect. Like exoplanets, their direct observation is almost impossible. Generally, they are detected by infrared observations of the sky. If you have some knowledge of physics, you know that electromagnetic waves in the infrared range are emitted by cold bodies, unlike ultraviolet. They therefore constitute the majority of the electromagnetic spectrum of brown dwarfs. Generally, these stars have an average surface temperature between 720 and 2200 degrees Celsius, or between 1,328 degrees Fahrenheit and 4,000 degrees Fahrenheit. But the coldest of them can even have a temperature below 200 degrees Celsius, or below 392 degrees Fahrenheit. For comparison, the surface temperature of our Sun is 5,500 degrees Celsius, or 9,932 degrees Fahrenheit. Other blue stars, much hotter, even exceed 9,700 degrees Celsius, or 17,500 degrees Fahrenheit. Some brown dwarfs have also been detected by coronography. This method consists in masking the light of a bright body like a star to let other stars appear more clearly. Also used for the detection of exoplanets, this technique has allowed the discovery of the first brown dwarf in history, Gliese 229b. The existence of brown dwarfs had been predicted since the 1960s, but it is in 1995 that Gliese 229b was revealed to the world. Until then, it was hidden by its twin star, Gliese 229a, a body 1,000 times brighter than Gliese 229b, but half as massive as the Sun. Since then, the exoplanet hunting satellite TESS has allowed us to learn more about these mysterious brown dwarfs. Initially launched by NASA to detect exoplanets by the transit method, it has also been able to observe many brown stars. A striking fact specific to the observations of TESS is that these failed stars look strangely like Jupiter. This is based on a study of a binary system of brown dwarfs, located only 6.5 light-years from Earth. These are the closest stars of this type to our solar system. They are named Lumen 16A and Lumen 16B, respectively, after their discovery by astronomer Kevin Lumen in 2013. Their mass is about 34 times that of Jupiter for one and 29 times for the other. Both possess a temperature of about 1,000 degrees Celsius or 1,830 degrees Fahrenheit. But what fascinates researchers is the presence of an atmosphere on these strange stars. Observations reveal cloudy bands on their surface, like those found on Jupiter. These bands betray the presence of extremely violent winds blowing at high speed. These winds could thus mix the atmosphere and redistribute the heat of the star. This is reminiscent of the impact of ocean currents, such as the Gulf Stream and the jet stream, on the weather of our planet. Today, these brown dwarfs are still being studied. These aborted stars are interesting because they allow us to learn more about the formation of atmospheres outside our solar system. But they are also important for understanding the process of star creation and the conditions necessary for the fusion of atoms. If brown dwarfs are invisible stars at first sight, their luminous equivalent populates the cosmos in large numbers. There are, of course, red dwarfs. These small stars, not very massive and relatively cold, have indeed succeeded in their ignition. It is estimated that they represent 80% of the stars in our galaxy, and it is likely that this is also the case for neighboring galaxies. Yet none of them are visible to the naked eye from Earth. The reason is that red dwarfs, although numerous, are very faint. At best, their luminosity is 10% of that of the Sun, and their mass is between 0.075 and 0.4 solar masses. As for their surface temperature, it is less than 3,800 degrees Celsius, or 3,870 degrees Fahrenheit. Not much to be impressed about. However, a detail about them should make you change your mind. Indeed, red dwarfs have an incredibly long lifespan, even on the scale of our universe. They can shine in the cosmos for hundreds of billions of years. But how to explain such a long life? Well, for that, we must look at the nature of these stars. Like all their cousins, red dwarfs are mainly made of hydrogen. This hydrogen is then transformed into helium, and then into other heavier elements, thanks to nuclear fusion, which results from the immense force of gravity at the heart of stars. We speak of nucleosynthesis, that is, the creation of new elements. Helium is created by the fusion of hydrogen. But for red dwarfs, this process is very slow, because these stars are essentially convective by nature. This means that helium cannot accumulate in the core of the star, but circulates homogeneously in the body of the latter. This constant mixing of matter allows red dwarfs to conserve their helium reserves, thus ensuring their stability over time. Therefore, it is theoretically impossible that a star of this type has already reached the end of its life since the birth of our universe after the Big Bang. Another interesting fact about red dwarfs is their content of certain heavy elements. To date, we have not observed any red dwarf without metals. The presence of these elements indicates that red dwarfs did not form at the very beginning of the universe. They result from the death of the first-generation stars, much more massive, having been able to synthesize these elements from hydrogen. If you are fascinated by red dwarfs, you should know that the closest star to us ever detected belongs to this category. You know its name. It is Proxima Centauri. Also called Proxima Centauri, it is part of a triple star system called Alpha Centauri. Its distance is only 4.2 light-years from Earth. In fact, estimates say that in 30,000 years it will be only 3 light-years away from us. What to feed the hope of one day visiting this system so particular? This hypothesis is all the more interesting when we know that 3 exoplanets orbit Proxima Centauri. Moreover, one of them, named Proxima Centauri b, is located in the habitable zone of the star. Unfortunately, the chances that they could be a refuge for life are still very slim. Fortunately, there are other interesting candidates not so far from Earth. For example, Barnard's star. This small red dwarf, located in the constellation of Serpentarius, is a little less than 6 light-years from Earth. It is well known to astronomers for having the largest proper motion ever observed. This means that its displacement seen from the Earth is very significant compared to other stars. But like all red dwarfs, it remains invisible to the naked eye. Interest in Barnard's star was rekindled when in 2018, researchers confirmed the presence of a super-Earth near it. The presence of exoplanets in the vicinity of red dwarfs thus seemed to be quite common. That said, to maximize the chances of finding potentially habitable worlds, it makes more sense to point our telescopes in the direction of another type of star. Stars similar in every way to our Sun, the ones called yellow dwarfs. The yellow dwarfs are undoubtedly the stars best known to astrophysicists. Indeed, since our Sun belongs to this category, we can make direct observations of its behavior and its role in a planetary system. However, yellow dwarfs represent only 10% of the stars in our Milky Way. This low abundance is explained by their relatively short lifespan. It is estimated that these celestial bodies shine on average for 10 billion years. Compared to the hundreds of billions of years of red dwarfs, their yellow cousins are very short-lived. Also, yellow dwarfs are relatively massive stars. Their mass is between 0.8 and 1.2 times that of the Sun. Their creation requires the accretion of a large amount of matter, unlike red dwarfs that can form from small clouds of interstellar gas. They also transform hydrogen into helium in their core. This process creates a lot of energy, which explains their high luminosity. Moreover, scientists have been trying to recreate the fusion process for many years. In the heart of nuclear power plants, it is not fusion but fission that is used. Instead of creating a new element from two atoms, fission involves splitting a heavy atomic nucleus into two lighter ones. This process, even if it generates a large amount of energy, is far from reaching the performance of fusion. But let's get back to our stars. Because of the astronomical temperatures and pressures they generate, yellow dwarfs generate thermonuclear fusion processes, creating heat and luminosity. It is estimated that the surface temperature of yellow dwarfs varies between 5,000 and 6,000 degrees Celsius, or between 9,000 and 11,000 degrees Fahrenheit. They are mainly composed of helium and hydrogen, but they also contain heavier elements in fairly small quantities. For example, our Sun is composed of 74% hydrogen, 24% helium, and 2% of heavier elements called metals in astronomy. As we have just seen, yellow dwarfs are not very common in the cosmos. But luckily, a star of this type is one of our close neighbors. We were just talking about Proxima Centauri. We have seen that it belongs to the triple system of Alpha Centauri. And one of the other two stars in this system, called Alpha Centauri A, is also a yellow dwarf. Seen from our Earth, its light totally eclipses that of Proxima Centauri. Its radius is 23% larger than that of the Sun. Its mass is also 10% larger. This is due to an abundance of heavy elements, twice as present in Alpha Centauri A. Currently, no planet has been discovered orbiting Alpha Centauri A. But in fiction, you may know a gas giant orbiting this star. It is called Polyphemus. It is this planet that you can observe in the sky of the moon Pandora, the place where the fiction Avatar, created by James Cameron, takes place. If the cosmos fascinates astrophysicists, it also inspires artists, whether they are painters, writers, or directors. Unfortunately, if one of the satellites of Polyphemus did indeed harbor life, it would end sooner or later. This tragic fate is also the one that the Earth will know. The reason is simple. Yellow dwarfs are not eternal. The day will come when they will have consumed all their hydrogen. At that moment, they will become fearsome red giants, devourers of worlds of titanic proportions. Have you ever dreamed of traveling through time to observe the birth and death of stars? If so, the good news is that these stages are visible from Earth. To see what our Sun will look like in its old age, let's go to the constellation of Orion. This is where Betelgeuse is located. one of the most famous red giants, among the brightest in the sky. Although scientists are not sure of its distance, they estimate that it is about 500 light-years from Earth. Far enough away not to worry us, but close enough to be observed. And for good reason. Its radius would be about 1,000 times larger than that of the Sun, making Betelgeuse one of the largest stars ever discovered. It is even in the category of red supergiants. If by some unfortunate chance it were to take the place of the Sun, its radius would extend between the orbits of Mars and Jupiter. Because of its immense size, Betelgeuse radiates more than 100,000 suns combined. However, originally, this giant was not so different from our Sun. But then what exactly happened? Well, to understand it, we must once again dive into the heart of this star. Initially, Betelgeuse was mostly made of hydrogen, just like the other stars. But after transforming all the hydrogen in its core into helium, the expansion of the star suddenly stopped. And a new force came into play: gravitation. Helium being heavier than hydrogen, the force of gravity took over, so that the core of the star began to contract on itself. At this point, the pressure and temperature soared to over 100 million degrees. Once this limit was crossed, it was the turn of the helium to fuse. Thus, in the heart of Betelgeuse, helium atoms condensed to form carbon, producing a phenomenal amount of energy in the process. This energy radiates so strongly that it causes the star to expand like a balloon. The outer layers are removed from the core and begin to cool. The star loses its bright yellow glow, giving way to an orange-red color. This phenomenon explains the size but also the color of red giants. Then, there are mainly two possible ends for these stars. If the mass of their core is less than 1.4 times that of the Sun, the fusion process stops once the helium is exhausted. The carbon core gradually becomes inert, and the star slowly dies. Due to the stellar winds caused by the pulsations of the core, the outer layers dissipate and are illuminated by the residual light of the star. The red giant thus gives way to beautiful stellar clouds called planetary nebulae. These clouds will continue to disperse slowly for hundreds of thousands of years. They will be the only remnants of the past presence of these ancient glowing stars, although not quite. Indeed, there will also remain the heart of the star, which will testify of its past presence. This core, once all the helium has been consumed, will contract and heat up even more until it causes the carbon to melt. It is then that rarer elements such as neon, sodium, or magnesium will appear. It is these new fusion reactions, very energetic, that will create the thermal pulsations, giving rise to ejections of matter. Eventually, the core will be unable to sustain the fusion reactions. Its heat and its density will be such that it will become unstable and will end up contracting on itself. This is how white dwarfs are born. This is what our Sun will look like in 7 billion years. But for stars whose mass is greater than 8 times that of the Sun, like Betelgeuse, the scenario is different. The collapse of the core causes an extremely rapid fall of matter towards the heart of the star. The core is so dense that the collapsed elements bounce off it, creating a gigantic explosion. You know the name of this phenomenon: supernovas. These explosions of stars are among the most violent events in the cosmos. Seen from Earth, the luminosity produced is such that it can lead us to believe that a new star has appeared in the sky. But in reality, it is the end of a very massive red giant. Later, we will see that there are still other possible endings for large stars. But before that, let's make another stop to observe the famous white dwarfs in more detail. After their disappearance, red giants often give way to white dwarfs. But what mysteries are hidden behind these small stars of light? To find out, let's visit one of our neighbors. Sirius B, close to 8 light-years from Earth, is a white dwarf. It is the remnant of a star, formerly similar to the Sun, having ended its life as a red giant. Like all white dwarfs, its density is extreme. To give you an idea, Sirius B has about the mass of the Sun, nearly 2 billion tons. On the other hand, its size is equivalent to that of our beautiful blue planet. According to observations, its density would be 2,000 kilograms per cubic centimeter. This is about the equivalent of a car in a thimble. In about 5 billion years, our Sun will become a red giant, then a white dwarf. This dwarf will be the size of a planet like the Earth, but it will retain 1/3 of the current mass of the Sun. It should be noted that white dwarfs have similar proportions and densities as a whole. To understand this uniformity, we must look at the physics. Indeed, white dwarfs are in their perpetual balance between pressure and gravity, just like classical stars. The more massive a dwarf is, the greater the pressure and density required to resist the forces of gravity. But for a mass too large, it is gravity that eventually prevails. A physicist named Chandrasekhar has therefore proved that the core is able to resist collapse only if its mass is less than 1.4 times that of the Sun. This is called the limit of Chandrasekhar. This is why only stars of about 8 solar masses maximum reach the stage of white dwarf. For more massive stars, the possible endings are much less gentle. As they die, these giants leave room for other mysterious artifacts of the cosmic bestiary that we will soon discover. Also, white dwarfs are quite difficult to detect. In the case of Sirius B, it was not directly discovered. Astronomers first observed its neighbor, Sirius A. The two stars form a binary system. It is by observing inconsistencies in the movements of Sirius A that scientists have deducted the presence of another body nearby. They then made calculations and were able to observe the small Sirius B at the theoretical location expected. It was thus the first star of this type to be photographed. If white dwarfs are so difficult to detect, it is because their luminosity is very low. NASA even explains that some are no brighter than a 100-watt light bulb, Indeed, white dwarfs can be very bright at their beginning, but having no more energy source, they slowly cool down. They then lose their brightness and heat, turning from white to black after a few billion years. At this stage, they become theoretically as cold as the sidereal vacuum. The internal structure of the white dwarf also changes with time. At the very beginning, just after the collapse of the star, the dwarf is still very energetic. Ions and electrons move freely at speeds close to the speed of light. But with the progressive loss of heat, the ions lose this mobility. They then rearrange themselves to form crystalline networks. Thus, an important part of the volume of white dwarfs would be a kind of giant diamond. Unfortunately, the structure of this crystal would be different from that of the diamonds found on Earth. Thus, do not expect to make a fortune by mining the heart of a white dwarf. Also, this structural change does not affect the size of the star, or at least what is left of it. All white dwarfs are thus doomed to become black dwarfs. Black dwarfs are nothing more than white dwarfs that have progressively cooled down until they no longer emit visible light, or almost. Moreover, they do not give off any significant heat, which makes their direct observation impossible. Black dwarfs are therefore even more difficult to detect than white dwarfs. To date, their existence is only theoretical. No black dwarf has ever been detected directly or indirectly. The easiest way to prove their existence would be to directly observe some stars whose motion does not seem to fit the theoretical trajectories. Such an observation would mean that a massive object is in the vicinity, deviating the course of the body by gravitational effect. This is how objects such as the black hole at the center of our galaxy, or planets like Neptune, have been discovered. But even if we try to detect black dwarfs in this way, the chances of finding them remain very small. For the simple reason that the cooling of white dwarfs is very slow. This process takes billions of years, just like the death of red dwarfs. However, the estimated age of our universe is only 13.8 billion years. It is therefore very unlikely that a black dwarf is already formed, even if it is from the first generation of stars to have come into existence. However, some people claim to have discovered black dwarfs not long ago, but further observations revealed that they were in fact brown dwarfs. Although quite similar, remember that brown dwarfs are not completely extinct stars. Rather, they are so-called failed stars, never having fully completed, remaining forever deprived of their brightness. Their mass is insufficient to initiate thermonuclear fusion reactions. Are we therefore condemned to never observe black dwarfs in our lifetime? Unfortunately, the answer is most likely yes. That being said, some researchers remain optimistic. This is the case of theoretical physicist Matt Kaplan, working at the University of Illinois. He hypothesizes that over very long periods of time, the effects of quantum mechanics would allow certain particles to cross the energy barriers of the remains of stars. This would allow the initiation of nuclear fusion reactions, making brown dwarfs detectable. To make an analogy, we can compare black dwarfs to the ashes of a wood fire. Inert, cold, and without light, these ashes can still cover tiny embers still glowing. Another interesting fact about black dwarfs, or brown dwarfs, is related to dark matter. To date, dark matter is one of the tracks we have to explain the structure and physics of galaxies. It also explains the velocities of some stars at the edge of our Milky Way. However, no one has ever succeeded in identifying this hypothetical dark matter, so that it still escapes our understanding today. It is even possible that dark matter is a totally erroneous hypothesis, just like the Aether hypothesis in its time. In the 19th century, scientists did not understand how light could propagate in interstellar space without a physical medium to carry it. They suggested that the entire cosmos was in fact bathed in the ether, a kind of invisible fluid allowing the light to propagate. The Michelson-Morley experiment later invalidated this thesis, and scientists like Maxwell or Einstein will highlight the duality, wave-corpuscle of light. It behaves both as an electromagnetic wave and as a corpuscle. All this mixed with a theory of relativity, thus explaining the misunderstood observations of the time. But let's get back to dark matter. Its nature is unknown to us, so that over time many explanations have been proposed. Among them is the invisible baryonic matter hypothesis. This one explains that dark matter would not be unknown, but that it would simply be a set of bodies and stars that escape our vision, like black holes, neutron stars, asteroids, brown dwarfs, but also black dwarfs. Thus, dark matter would simply be matter as we know it, but that we have not yet observed. Unfortunately, this hypothesis was quickly invalidated. With the discovery of fossil radiation, that is, the first photons emitted in the observable universe, we know with precision how much baryonic matter is in the universe. And this amount is insufficient to replace the effect of the mysterious dark matter. In our lifetime, it is therefore almost certain that we will never find a black dwarf. Moreover, even our distant descendants will have little chance of detecting one day, as the process of extinction of a white dwarf is so long. These dead stars are therefore condemned to remain mere hypothetical objects for us. But rest assured, the universe still holds many mysteries that we will discover. Not to mention that until now, our journey has only led us to the most common types of stars. It is therefore time to go and visit much less ordinary stars, but also much more spectacular. Our sun is far from being the biggest star in our galaxy, and in a way that's great news. Its mass and temperature are just right to provide us with heat and light for hundreds of millions of years to come. If it had been bigger, it is very likely that life would never have developed on Earth. Also, the sun would have been much more ephemeral. We know this only too well because hypermassive stars with a very short lifespan are hidden in our Milky Way. They are called blue giants. The name is not insignificant since it describes perfectly the nature of these stars. Blue giants are monstrous stars whose size and temperature are beyond comprehension. If the diameter of our sun is about 1.4 million kilometers or 870,000 miles, the diameter of a blue giant ranges from 10 million to several hundred million kilometers, or from more than 6 million to a few hundred million miles. The mass is on average 8 to 10 solar masses, and their temperature is well over 10,000 degrees Celsius or 18,000 degrees Fahrenheit, compared to about 5,800 degrees Celsius or 10,500 degrees Fahrenheit for our Sun. By the way, what about going to observe one of these giants? To do this, we must go to the constellation of Orion, about 900 light-years from Earth. This is an extremely far distance, and yet we can see the star there from Earth. This cosmic titan is none other than Rigel, a blue supergiant known as the sixth brightest star in the sky. About 80 times larger than our Sun, it is also 40,000 times brighter. But this applies to the light emitted in the visible spectrum. If we added the light emitted in the ultraviolet, Rigel's luminous power is 60,000 times greater than that of the Sun. These characteristics are simply outrageous. But rest assured, blue giants such as Rigel are quite rare in our galaxy. Their formation requires immense quantities of matter, which explains their rarity. Their lifespan is also quite short, only 10 to 100 million years. In comparison, the lifespan of the Sun is estimated at 10 billion years. Indeed, the stages that punctuate their life cycle are more or less the same as those of other stars. However, because of their immense size, they exhaust their energy reserves very quickly. At the end of their life, they become red supergiants, even more impressive. Because of their size and brightness, blue giants are quite easy to spot, unlike red dwarfs, which are much more numerous. Rigel's color, like that of other blue giants, is again explained by its temperature. At its surface, Rigel burns at more than 10,000 degrees Celsius, or 18,000 degrees Fahrenheit. This heat explains why its radiation tends towards blue, where smaller and cooler stars tend towards red. When Rigel has burned off much of its hydrogen reserves, it too will begin to swell, lowering its surface temperature. It will then become a red supergiant before going out in a final burst of light, a supernova. So far, our journey has led us to stars of many colors. For the stars around 3,000 degrees Celsius or 5,500 degrees Fahrenheit, the main color was red. For those around 4,000 degrees Celsius or 7,200 degrees Fahrenheit, it is rather orange that dominates. For stars similar to our Sun, those whose temperature is between 5,000 and 6,000 degrees Celsius or 9,000 degrees Fahrenheit, their main color is yellow. Even hotter, the stars of about 10,000 degrees Celsius or 18,000 degrees Fahrenheit are white, even slightly bluish. Finally, the hottest stars, over 20,000 degrees Celsius or 36,000 degrees Fahrenheit, range from light blue to deep blue. But one color seems to be missing. If you pay attention, you will notice that no green star has been mentioned. But then, where are the jade stars hiding? If we look at the visible spectrum, we notice that the wavelengths associated with the color green are halfway between the yellow and blue wavelengths. Shouldn't stars of intermediate temperature be green rather than white? Well, to understand this phenomenon, we must go back to the color classification of stars. To tell you the truth, these are oversimplifications. They are therefore partly false. Stars are not totally red or totally blue. They emit wavelengths in a very wide spectrum, including invisible wavelengths, such as X-rays, infrared or ultraviolet. They also emit in all visible wavelengths. Thus, blue giants also propagate red light, yellow light, and of course, green light. However, depending on the temperature of the star, the proportion of these colors varies, so that very hot stars emit more blue light than red light. Now, for the stars of intermediate temperature, they emit shares of green light, blue, and red about equivalent. Thus, these different colors of light combined to form white. In physics, white represents the set of mixed colors, while black is the absence of colors. In other words, stars are always multicolored, but with a tendency to tip towards red or blue. Stars that could be called green exist, but our eyes are simply unable to distinguish them. This explains why they appear white to us. In reality, the explanations are a little more complex. We must also take into account the composition of our atmosphere, which diffuses and refracts light. In fact, the sun sometimes appears yellow, sometimes white, or even orange when it descends towards the horizon. In some very rare circumstances, the last glimmers of the sun can even be completely green. This phenomenon occurs at the very first moments of a sunrise or sunset. Under particular atmospheric conditions, blue light is diffused into the atmosphere. The red light is refracted below the horizon, so that most of the green light remains, giving rise to a rare phenomenon called green ray. However, this optical phenomenon is very brief. The chances that you will be able to see it one day are therefore slim. Anyway, you now know why green stars are not included in the classification of colors according to temperature. The spectroscopy of stars is a vast subject, and there is much more to say about it. But our journey is not over yet. So let's get back on the road to our next destination. After crisscrossing the galaxy and traveling millions of light years, it's time for us to travel through time. We were able to observe the different types of stars and the physical laws that explain their behavior. To put some order in all this, we must go back to observe the birth of a star. For this destination, we will stay in our own solar system. Let's go back about 5 billion years to witness the birth of the latter. At that time, there was neither planet nor sun, only an interstellar cloud of gas and dust called solar nebula. Under the effect of gravity, this cloud of gas condensed until it rapidly collapsed on itself. This phenomenon is called gravitational collapse. The denser parts of the nebula began to concentrate. Smaller, denser clouds of gas and dust then formed in various places. As the gravitational forces were higher at these locations, the hydrogen atoms began to combine to form dihydrogen molecules. We speak then of molecular clouds. But for the sake of popularization, they are more generally presented under the name of nurseries of stars. Thus, the temperature and pressure continued to increase under the effect of the collapse. So much so that beyond 3,000 degrees Celsius or 5,500 degrees Fahrenheit, the molecules of dihydrogen split in two. and between 6,000 and 10,000 degrees Celsius, or between 10,800 degrees Fahrenheit and 18,000 degrees Fahrenheit, the electrons and protons ended up separating. This very unusual state of matter is called plasma. The collapse and heating phase lasted hundreds of thousands of years. It is during this period of time, very long to our eyes, but instantaneous on the scale of the universe, that an embryo star was formed, a protostar. Our sun was beginning to appear, but it could have been otherwise. After the formation of a protostar, three scenarios are possible. The most massive clouds give rise to the birth of giant stars, whose mass is 8 times that of the Sun at least. Conversely, smaller stars such as red or brown dwarfs may emerge, and in a third case, stars of intermediate sizes come into the world. This is the case of our Sun. The most massive stars die quickly. They turn into red supergiants and eventually explode into Type II supernovas. As for the smallest stars, they can shine for hundreds of billions of years and are not yet extinct. Our Sun is halfway between these two life courses. First protostar, it continued to concentrate until its temperature and internal pressure became high enough to initiate nuclear fusion. For this, it had to cross the symbolic threshold of 10 million degrees Celsius or 18 million degrees Fahrenheit. At this stage, the internal pressure of our nascent sun had become strong enough to counterbalance the gravity that compressed it. It then entered a phase of stability called main sequence. It began to radiate into the cosmos, bathing the surrounding area with its light, and gradually warming the sidereal void around it. Under the effect of its strong gravity, the surrounding matter that had not been absorbed began to gravitate around our young star. By accretion of matter, the planets gradually began to take shape until they ended up in the solar system we know. You might as well say that at this period of high activity, it was not good to live on Earth. As we saw earlier in our epic, stars shine thanks to nuclear fusion. Thus, for almost 5 billion years, the core of our sun has been acting as a cosmic nuclear reactor. Inside, the temperature is more than 15 million degrees Celsius, or 27 million degrees Fahrenheit. This is the hottest point of our star, and therefore, it is the only place where the fusion process can take place. The hydrogen atoms fuse to form helium atoms. The core of our sun is therefore the source of the energy it releases, and yet it represents only 1% of its volume. On the other hand, the density of the core is such that it accounts for about 1/3 of the total mass of our star. Even more fascinating, the fusion reaction of hydrogen atoms, apparently simple, is in fact of great complexity. Indeed, hydrogen atoms are only made of a proton and an electron. However, helium atoms are made up of 2 protons, 2 electrons, but also 2 neutrons. The question is therefore, where do these famous neutrons come from? In reality, they come from hydrogen itself. Under extreme conditions, hydrogen protons can be transformed into neutrons by a process called beta decay. For each proton thus transformed, 2 subatomic particles are emitted, a positron and a neutrino. Neutrinos have the particularity of not interacting with matter. the latter are emitted and leave to roam freely in space. But positrons are antimatter particles. They are the exact opposite of electrons, so that when these two elements cross paths, they cancel each other out in a tremendous explosion of energy, and thus create heat. To return to our protons, once they become neutrons, they bind with another proton of a hydrogen atom, forming a new element, deuterium. The deuterium then becomes helium-3, and two helium-3 atoms combine to form helium-4, the most common form of helium. This whole process is summarized under the term proton-proton reaction chain. The stars, which are then associated with incandescent gas giants, are much more complex than their appearance suggests. They are actually closer to a nuclear plasma reactor than to a giant fireball. Fortunately, stars are not very efficient nuclear reactors. It may seem paradoxical, but in proportion to their volume, the fusion reactions that take place are quite rare. This explains why they can shine for several billion years. This is also why more massive stars die faster. Their cores are denser and hotter, so fusion reactions are much more frequent. Hydrogen is then depleted much faster, leaving room for helium fusion, red giants, and finally, white dwarfs. We described this process during our stopover near the red giant Betelgeuse. However, we had seen only a part of the possible ends for this type of star, namely, their disappearance in planetary nebula and the transformation of their heart into white dwarf. But for the more massive stars like Betelgeuse or the famous blue giants, things get more complicated. Dear travelers, it's time for us to head for much more hostile areas of space. Get ready, because now we are going to talk about immeasurable cosmic events. We are going to witness the fall of some giants, which for their last breath emit more light than 1 billion suns. When a supermassive star dies, it produces a cataclysmic explosion, a supernova. The luminosity released during this event can then exceed that of an entire galaxy. There are two types of supernovas, Type 1a supernovas and Type 2 supernovas. For the massive stars that we are talking about here, those whose mass is greater than 8 times that of the Sun, it is the Type 2 supernovas that occur. As the fusion reactions continue, all the elements such as helium, carbon, or oxygen are eventually exhausted. At some point, the resulting heat of fusion no longer produces enough pressure to counterbalance gravity. This force then begins to compress the core of the star. At this point, the fusion resumes. However, it is no longer the fusion of 2 atoms that occurs. Each atom begins to fuse individually, electrons combining with protons to form neutrons. When only neutrons remain, they continue to compress again and again until they reach their limit. The core cannot compress any further. This sudden stop of the contraction causes a phenomenal shock wave, giving rise to an immense ejection of matter. The outer layers of the star are then blown into space. This is the supernova. The collapsed core of the star can then give way to a neutron star. But for the most massive stars, their disappearance leaves room for another cosmic element, now known to all, a stellar black hole. Supernovas, it is important to know that this is probably the most powerful type of cosmic explosion, at least after the Big Bang. The energy released can reach 10,111 joules, or a 1 with 111 zeros behind it. To give you another more telling example, the atomic bomb dropped on the city of Hiroshima during World War II had a power of only 1,013 joules. Even a cosmic event as powerful as a solar flare is only 1/1000th of a billionth of the power of a Type II supernova. This is what is likely to happen to our dear Betelgeuse. This one being a red hypergiant, it will surely explode when it runs out of fuel, producing in the process several billion times the energy of the Sun during its lifetime. Fortunately, these supernovas are quite rare, and it is unlikely that we will ever fall victim to their blast. That said, if Betelgeuse were to explode in our lifetime, it would be visible from Earth, despite the 640 light-years that separate us. It would then remain shining in the Earth's sky, and would even be visible during the day. You should know that there is also another type of supernova, less powerful but more common. These are the Type 1a supernovas. These occur because of white dwarfs. A priori harmless, white dwarfs are nevertheless dangerous when they are near another star. In a binary system, a white dwarf can continue to accrete matter because of its strong gravitational attraction. In a way, it can be said that it vamps its neighboring star, which has the effect of increasing its mass. And when it becomes too massive, more than 1.4 times the mass of the Sun, it exceeds the limit of Chandrasekhar that we mentioned earlier. It is then that the problems begin. The collapse resumes, leading inevitably to the explosion of the dwarf star in a supernova of Type 1a. In this case, the power released is staggering again. But the magnitude of the event is undeniably smaller than that of a Type II supernova. The estimated power of a Type 1a supernova is about 1,045 joules. Nevertheless, these powerful detonations of stars, although destructive, leave a magnificent spectacle. It marks forever the fabric of interstellar space of a scar of beauty called nebula. Direct observations of a supernova, of which we still keep written records today. A chance when we know that supernovas occur only once every 30 years in our Milky Way. Among them, many escape observation. Type II supernovas are certainly much more visible, but also much rarer. They have never been directly observed during the last decades. However, their remnants, including the famous nebulae, remain visible for thousands of years. This is also the case for the neutron stars that we mentioned earlier. These very peculiar stars are the equivalent of white dwarfs for other stars. However, their characteristics and the mysteries they contain arouse our curiosity. So let's continue our journey to observe them more closely. Once they run out of fuel, stars larger than 8 solar masses become unstable. The fusion in their core no longer takes place. Nothing opposes gravity, and the star begins to collapse on itself. It is then that their core compresses. The core shrinks, and its temperature soars, reaching several billion degrees. In these extreme conditions, the laws of physics as we know them no longer apply. Matter becomes more and more agglomerated, so much so that electrons merge with the core of atoms. Protons and electrons disappear to form neutrons. The neutrons are compressed as much as they can until they create the supernova. Thus, behind this tremendous explosion, there is always the heart of the star, now only made of neutrons. Hence the name, neutron star. As you can see, these stars are in fact the corpses of hypermassive stars. Their density is simply staggering, given that they are formed of an incompressible matter, or almost. Imagine the mass of a sun in a sphere of 10 to 20 kilometers in diameter, or 6 to 12 miles in diameter. A star like Pluto, if it had the same density as a neutron star, would not be bigger than a bacterium. Hard to imagine, isn't it? In addition, it sometimes happens that planets or stars from a binary system continue to orbit neutron stars, and this despite the blast of the supernova. This shows the importance of the force of gravity. Such an importance that if the neutron star was compressed further, the star would turn into a stellar black hole. This is what happens with the most massive stars, although it is quite rare. As you might expect, neutron stars are extremely hot. Some exceed 1 million degrees Celsius at the surface, or over 1.8 million degrees Fahrenheit. The collapse of the original star also accelerated the core's rotation rate. Because of their small size, neutron stars rotate on itself at tremendous speeds, close to the speed of light. This is equivalent to nearly 1,000 rotations per second. As with black holes, the tidal forces and time dilation near neutron stars are extreme. They act like gravitational lenses, bending the light that would have the misfortune to cross their path. Because of their incredible density, the core of neutron stars, like that of black holes, remains a mystery to science. Astrophysicists are able to predict the behavior of matter on the periphery of these stars thanks to the laws of quantum physics. Atomic nuclei, electrons and neutrons arrange themselves together to form layers with very different structures. Because of their different shapes, these are called nuclear pastes. Because, like the pasta we are used to cooking, they can take various shapes, which facilitates their classification. But all this is still a theory. It is even possible that we will never understand the mystery of neutron stars. However, one thing we do know for sure is that neutron stars have extremely strong magnetic fields. These fields are generally not aligned with the axis of rotation of the star. At the north and south poles, beams of very powerful electromagnetic waves are emitted and sweep across the cosmos at regular intervals, and when one of these beams crosses the Earth, we can detect it. This sweep being periodic, the phenomenon repeats itself in time. Neutron stars propagating their waves towards us are called pulsating stars. These pulsating stars are classified according to their speed of rotation. The faster they rotate on themselves, the faster they will blink from our point of view. These speeds are also correlated to the type of waves produced by the pulsars. While most of them send us radio waves, the fastest ones emit X-rays and even gamma rays. The most powerful of them are even called magnetars, but their strange behavior is still poorly understood. Like everything else in our universe, pulsars are subject to the ravages of time. Thus, as they gradually lose energy through radiation, they eventually lose speed, until they are only spinning a few times a minute. Nevertheless, pulsars remain very useful in astronomy, especially because they provide us with very precise time references on the cosmic scale. Nevertheless, pulsars remain very useful in astronomy, especially because they provide us with very precise time references on the cosmic scale. In general, neutron stars are of crucial importance for understanding the effect of extreme densities on the behavior of matter. They are thus used to flesh out the theory of quantum physics, and even that of general relativity. Who knows, maybe the key to unify these two great theories is in fact in the heart of neutron stars. While waiting for further discoveries, we can only admire these fascinating stars with their extraordinary properties. Our journey in space has led us to many stars with very different characteristics. Sometimes old, sometimes new, sometimes huge, sometimes tiny. These stars are much more diverse than we could have imagined. Now it is time to move on to even stranger stars. Strange stars that sometimes remain mysteries for science. And for that, what better way than to discover vampire stars? Under this terrifying name are hidden stars that are less at first sight. Remember the white dwarfs. We had seen that their destiny was to end up as black dwarfs after a long and tedious degeneration. But some seem to have not said their last words. It is not unusual for white dwarfs to be part of a binary system. They remain accompanied by a star which is still in its main sequence. But what is our white dwarf doing in these conditions? Well, if its proximity and its force of attraction are sufficient, our white dwarf can literally tear matter from its neighboring star. It then forms an accretion disk around it. This increase in matter significantly increases the temperature of our dwarf, although it is intended to cool. The temperature can rise to more than 100 million degrees Celsius, or more than 180 million degrees Fahrenheit, and under these conditions, nuclear fusion can resume. If the white dwarf manages to suck enough matter from its companion, a Type 1a supernova is produced. This is what we explained earlier. After the explosion, our white dwarf becomes a neutron star. But in other cases, this process never comes to an end. The white dwarf sucks in matter, but before the supernova can form, a similar, less powerful phenomenon occurs. This is simply called a nova. The white dwarf remains intact after having expelled the sucked matter, and starts again to devour the accompanying star. And the nova repeats itself again and again. This is notably the case of RS Ophiuchi. This white dwarf, located in the constellation of the same name, is about 5,000 light-years from Earth. Since its discovery in 1898, it has already exploded 6 times in nova. The last explosion was in 2006, and it is very likely that this phenomenon will be repeated soon. More recently, a similar phenomenon was discovered in the Kepler telescope archives in 2020. The system at the origin of the event would be a binary system composed of a white dwarf and a brown dwarf, 2 stars at opposite ends of the spectrum. During the explosion, the luminosity of the system would have been multiplied by 1600. Under these particular conditions, the white dwarf is qualified as a cataclysmic variable star. But there are other types of variable stars whose discovery was a surprise for astronomers. Variable stars are stars whose brightness varies over time. In the long run, all stars eventually become variable. Indeed, during their main sequence, that is, during the majority of their life cycle, stars are stable. They maintain an equilibrium between their internal pressure, which tends to repel matter and gravity, which tends to compress the star. But at the end of their life, when they become red giants, things get complicated. The balance is broken, and the star expands. The outer layers lose heat, the temperature drops, and the luminosity also. However, gravity takes over the dilation periodically. At this time, the pressure and temperature increase, and the star regains its brightness. It is therefore not uncommon to observe variations in brightness in red giants. When these variations are very important, it may be the beginning of the spectacular explosion of the star. This was the case for Betelgeuse. Yes, again. In 2020, the red supergiant has experienced a sharp decline in brightness. Scientists then hypothesized that it could explode into a supernova soon. A real surprise for astronomers who already saw a supernova live. Remember that such an event has not been observed directly for several centuries now. But was this really the beginning of the end for Betelgeuse? Well, no. This one still seemed to have a lot of good days ahead of it. So what exactly happened? From January 2019 to March 2020, the giant's brightness kept dropping. Then suddenly, it became normal again in April 2020. Did Betelgeuse make us an April Fool? In a way, this is what happened, but the prank was not intentional. The star was simply partially obscured by a cloud of gas and dust. A rather surprising discovery, especially when we know that Betelgeuse is at the origin. Indeed, due to its instability, it would have emitted a huge bubble of gas, which while cooling, would have condensed, trapping the surrounding dust. An opaque cluster has thus formed in front of the red giant, obscuring its surface. This surprising phenomenon is quite unusual, which explains the incomprehension of scientists during the first observations. But changes in luminosity due to ejections of matter also concern other stars grouped under the term eruptive stars. It also happens that a star is partially obscured by other bodies in orbit. This happens in binary systems, where two stars pass successively, one in front of the other. It is also the case when a planet passes in front of a star from our point of view. Moreover, this is how many exoplanets, invisible at first sight, were detected by the transit method. Thus, variable stars are generally divided into two categories. One, intrinsic variable stars, whose luminosity variations are due to phenomena specific to the star. Two, and extrinsic variable stars, whose variations are caused by an external source. Once again, all this shows us how complex stars can be. They are inexhaustible sources of enigma and fascination, and they allow us to learn more about the laws that govern our universe. This is true for one last kind of star that we have not yet talked about. So for the last stop of our interstellar journey, let's isolate ourselves in the confines of our galaxy. For it is here, far from any form of activity and matter, that the lonely stars are hidden. Most stars are formed in nurseries. Within these so-called molecular clouds, the brightest stars can be born until they gradually form complex systems composed of planets, planetoids, and other asteroids. But not all stars are so lucky. By an unfortunate twist of fate, some stars find themselves isolated, doomed to drift alone in the cosmos. These stars, qualified as loners, orphans, or wanderers, have aroused the curiosity of scientists. Is it possible that they were formed far from any source of activity, in cold and empty areas? And if so, how to explain such a mystery? To tell the truth, it seems unlikely. The most commonly accepted hypothesis is that these stars formed like all the others, in effervescent clusters. By lack of luck, they were then ejected from their birthplace until they were adrift in the universe. A fascinating place for the study of wandering stars is none other than the Small Magellanic Cloud. It is a dwarf galaxy located 200,000 light-years from Earth. The Small Magellanic Cloud is a kind of satellite of our Milky Way, just as the Moon is a satellite of the Earth. When we point our telescopes at this cloud, we realize that nearly a quarter of the massive stars in it are drifting stars. The most common explanation is dynamic ejection. This occurs when a star is expelled because it would have an unstable orbital configuration at the origin. As Newton's first law explains, for every body retains its state of rest or uniform motion in a straight line, in which it is, unless a force is applied to it. This is simply the principle of inertia. Thus, if no force is sufficient to keep a massive star in orbit, it ends up wandering in the sidereal void. The same is true if a large enough force manages to eject a star from its orbit. This can happen in a rarer case, that of a gigantic supernova. In the case of a binary system, when one of the two members explodes in a supernova, the common center of gravity can become too weak to maintain the second member in orbit. The latter is then adrift. Even more rarely, two stars may collide. These stars merge to form a single star with its own motion that leads to its ejection from the original system. Finally, the last case is when the stray star is formed directly away from the others. This process can occur when dense regions of gas and dust collapse to form stars. Unfortunately, these stars do not have enough mass to attract other stars and cannot form a binary star system. They are thus condemned to a long existence of wandering and solitude in the infinite void of space. Thus, our long journey comes to an end. This one will have allowed us to discover the different stars lurking in the cosmos, from the red dwarfs that populate our galaxy en masse, to the red giants that are waiting to breathe their last, to the brown dwarfs that have never managed to shine. Our discoveries have also allowed us to lift the veil on certain mysteries, notably the absence of green stars, which in fact results from our inability to isolate certain wavelengths. Let's also mention the black dwarfs that are waiting to be observed. And let's not forget the blue giants and red supergiants that give rise to the strangest stars, such as neutron stars and terrifying stellar black holes. Stars are wonderful. They are what give our universe its brilliance. They are necessary for life, as evidenced by our sun, warming the earth and giving rhythm to our daily lives. Perhaps there are other systems with other stars that are also home to life as we know it. But the role of stars is more extensive, for they enable the life of the universe itself. The fusion reactions that occur in their cores form new elements, giving rise to a tremendous diversity of matter. In an eternal cycle of creation and destruction, stars will continue to form and then fade away, sometimes in a huge cosmic firework display. Without them, the atoms that make up the planets, the objects that surround us, but also our own bodies would not be. So the next time you contemplate the starry sky, you may have a strange feeling. A mixture of fascination, vertigo, and gratitude towards these stars, far from having revealed all their secrets.